Welcome to video number 5 in Advanced Fluid Mechanics. So in this video, we'll be finishing off section 3, which is the conservation laws. And so I'm showing here the gray text is what we covered previously in video 4, and the white text is what we're going to be covering in this video here. We're just going to wrap up the conservation laws by looking at the mechanical energy equation, which we'll see is really an extension of our force balance. We'll do first law of thermodynamics, which leads us to our thermal energy equation. Then we'll look at an approximation you can make to simplify these equations called the Boussinesq Approximation. And we'll finish by looking at the boundary conditions, and then talk about how we would solve all the equations we derived here, and what it means to say that we'd solve these equations, and how would we use them. Okay, so let's look at what's called the mechanical energy equation. And what this is really is it's an equation for the kinetic energy of the fluid. And what we're going to look at in this section is what happens to the energy in a flowing fluid. And so we're going to look at, if you give energy to a fluid, how much of it goes to accelerating it versus how much goes to deforming it. And we're going to look at another term called viscous dissipation, which comes up a lot in advanced studies involving fluid mechanics. And so the goal here is to make sure we know what all these terms mean and we understand what's going on with the energy in a fluid. So to get this kinetic energy equation, what we do is we actually take a scalar product of the momentum equation and a velocity vector, right? So we're essentially taking the momentum equation. We remember it's a force balance per unit volume, right? So we have our equation of motion here as a force balance per unit volume, and we multiply that by velocity. Okay, and then just a quick aside about the notation here, where I've written this ui squared. Just make it clear that that's actually ui. So we're implying there's a repeated index there because it's squared. So that would actually equal this. Okay, now remembering back to our physics, right? We generally described energy as force times the distance through which it acts, right? So if we multiply instead by a velocity, multiply our force by a velocity, we end up with the rate of energy. Okay, so in this equation here, we multiply our equation of motion by ui, and now that gives us a rate of kinetic energy. And so we can see this term on the left here is saying the rate of increase of kinetic energy at a point equals the sum of what we have on our right-hand side, which is the rate of work done by a body force G, and the rate of work done by the net surface force per unit volume. Okay, now there are other forms of the mechanical energy equation and other ways to derive it, but what I want to focus on here instead of that, I want to focus on looking at how this kinetic energy can be lost to internal energy by deformation of our fluid elements, okay? Okay, so we're going to focus on this term here. And that is the velocity times the net force imbalance at a point due to differences of the stresses on opposite faces of our fluid element. So this net force accelerates the local fluid and increases its kinetic energy, right? But this is not the total work done by our stresses on the element, right? Because the remaining part can go into deforming the element without accelerating it, okay? The total rate of work done by these surface forces actually has to be represented by this term here, right? Because it can be transformed into a surface integral of our stress tau ij times ui over the element, okay? And we can split this up into two components. And so we've seen that this last term here, right, from our previous equation, results in an increase of kinetic energy of the element, but the rest of the work here can only deform the element and increase its internal energy, okay? Now we look more closely at this deformation work, and we can rewrite this by taking advantage of the symmetry of the stress tensor, which is something we've done before, right? Now because the stress tensor is symmetric, we know that if you multiply a symmetric tensor and an anti-symmetric tensor, you get 0. So the product of this is only, because this is symmetric, so the product is only going to be the symmetric part of this times the symmetric stress tensor, which is how we get Eij. Now for the stress tensor, we can sub back in the Newtonian constitutive equation that we developed in video 4, which is a relationship between our stress and our deformation. Okay, so we sub that in and we get this right here. And then we take this part right here, our viscous part, and we call that phi, and then rewrite it like this, and then rewrite this phi component. We can simplify it, right? Just like this down here. Okay, now what we're trying to do here is rewrite our energy equation in terms of this phi. So looking back here at our kinetic energy equation, we can substitute for this term here by using this equation, meaning we sub in this term and this term. Okay, so we do that right here, where we remember that this was substituted in for this one here, which then shows up here. And then expanding that deformation work out like this, right? So it becomes these two terms here. We'll have this expression. Now we're actually going to see these last two terms show up later when we look at our internal energy equation. So now we see that this viscous term phi is always positive, and that represents a rate of loss of mechanical energy and a gain of internal energy due to deformation of the element. This term here, so this total term here, represents the total deformation work rate per volume, and the part with the pressure, this term here, is the reversible conversion to internal energy by volume changes. And this part here is the irreversible conversion to internal energy due to viscous effects. So this quantity phi is proportional to mu, our viscosity coefficient, which we've seen down here in this equation, right? And this phi represents the rate of viscous dissipation of kinetic energy per unit volume. Okay, so as I mentioned, that's a term that comes up a lot, right? So now you know in a lot of detail exactly what that viscous dissipation is, right? And it's proportional to the square of our velocity gradients. We can see from looking down here in our bottom left there, right? Square of the velocity gradients. And therefore it's more important in regions of high shear. And this heat that we end up getting from this viscous dissipation, where it's converting our kinetic energy into this internal energy, that's going to show up as heat, right? So that could be like a hot lubricant in a bearing, or we might see that as the burning of the surface of a spacecraft on re-entry. So it'll be things like that where this viscous dissipation would show up as heat. Now, we've been looking at this in terms of kinetic energy as our form of mechanical energy. So we see that the effects of gravity appear as work done on a fluid particle. But we could also rearrange it, right? So the rate of work done by the body forces is moved to the left-hand side of our mechanical energy equation. And we can interpret it now as changes in the potential energy. So the body force can be represented as the gradient of a scalar potential, like this. So therefore this is true. And when writing the material derivative there, we note that we used the partial of gz with respect to t equals 0 because z and t are independent, okay? So we rewrite this equation here, right? Moving our potential energy over to the left-hand side, okay? And that's this equation here. Now, so our scalar potential function now has the significance of our potential energy per unit mass, which I'll note too, just for completeness, this identification is possible only for conservative body forces where we can write a potential. Okay, so all this helps us see and think about what happens to our energy, right? Where does our energy go? So one final thing we can do with this mechanical energy equation is to take an integral form of it. Okay, so we can integrate this over either a fixed volume or a material volume, right? Again, as we've done before in this course. So if we take a fixed volume, and we'll start with this equation here. I'm needing more and more colors as we go through this. So we take this equation here, and we've just rewritten the left-hand side where E equals rho ui squared over 2 is the kinetic energy per unit volume, okay? So we integrate each term of this equation over our fixed volume V. And another trick we've done before, right? The second term and the fourth term are in a flux divergence form, okay? So that when we do their volume integrals, we can change those into surface integrals by Gauss's theorem, okay? And then we rewrite the complete integral form as I've shown at the bottom here, where each term is a time rate of change. And I've also listed here how we can describe each of these terms. So that fourth term here represents the rate of work done by forces at the boundary, because the stress times our area is the force in the I direction, and then the force in the I direction times our velocity is a scalar product of the force with the velocity vector. Okay, so that's the rate of work done by the forces at the boundary. Okay, and the rest of the terms we've described before. So the rate of change of the kinetic energy, rate of outflow across the boundary, right? Rate of work of the body force. And then our deformation, right? The rate of work by the volume expansion, and our rate of viscous dissipation is all accounted for in our integral form there. Okay, so now we know what viscous dissipation is, right? And we know we can think a little more deeply about the energy associated with our fluid elements. That'll help us understand our fluid mechanics a little better, I hope. Okay, now that mechanical energy equation we just looked at was derived from the momentum equation, and so that's not a separate independent principle. Now in flows where we have temperature variations, we need an independent equation, and we get this from our first law of thermodynamics, which is essentially our energy balance. So we're going to let Q be our heat flux vector per unit area. E is going to represent our internal energy per per unit mass. Remember to be taking some notes here. I can also make a quick note that for a perfect gas, E equals CVT, where CV is a specific heat at a constant volume. And this sum here, we can think of as our stored energy per unit mass. And basically what this equation is representing is our first law of thermodynamics. And so one way to say this is, as I've written here, we can think of it that the rate of change of stored energy equals the sum of the rate of work done and the rate of heat addition to a material volume, okay? So we know we've got the work done by our body forces, right, included here on the right-hand side. Just note that we've got a negative sign right here because dA is outward normal to our volume. So Q dot dA there represents heat outflow. So the heat flowing outwards is a negative contribution, right? That reduces our stored energy. And heat inflow, therefore, would now be a positive term on the right, which would increase our stored energy, as we would expect. It's really helpful to look at all these terms and really understand what each of the terms themselves means and how they contribute. Because for different scenarios that you have, it may be that only certain terms dominate, right? And so you can really help simplify your problems that you're looking at by understanding which of these terms is really going to contribute. Now, to derive a differential form, we'll have to express all these terms in the form of volume integrals. So we can use our Reynolds transport theorem on this first term to convert it to this here. We then convert our two surface integrals into volume integrals, again, as we've done before. And the result is this equation right here. Okay, and this is the first law of thermodynamics in differential form, so we can actually just go ahead and box that. That's an important one, of course. And we can see that it has mechanical and thermal energy terms in it. And if we just wanted the thermal energy equation, right, so we can look at our previous section 3.9 and subtract the mechanical energy equation from this expression, and that would give us our thermal energy equation, which is commonly called the heat equation. That's this one right here. That one, of course, has to be boxed as well. That's the heat equation, very important. And what that says now is that's saying E is our internal energy, right? So on the left, we have the internal energy increases, okay, on the left-hand side, because of what's on the right-hand side, which is the convergence of heat, volume compression, and heating due to viscous dissipation, right? And these terms we saw previously in our mechanical energy equation, because that's the conversion of this kinetic energy into internal energy. So that's why in the heat equation, those have to be added so the signs are flipped, because now they're contributing to the internal energy equation. So again, that's our internal energy increases because of the convergence of heat, volume compression, and heating due to viscous dissipation. Okay, and again, depending on what types of problems you're going to look at, oftentimes this energy equation goes hand in hand with our advanced fluid mechanics equations. Okay, there's a lot of interrelationship between the energy and the flows, right? Oftentimes this field is referred to as thermal fluids. Okay, so it's really important to look at these energy equations as well. Okay, now the purpose of deriving all these equations from our conservation laws is to give us a way to solve for the behavior of our fluid. Okay, so when we think about the mass balance and the momentum equation, right, if we want to solve that for a specific domain, we're going to be solving for what the velocity values are. Okay, so we want to figure out the velocities of our fluid at each point in our domain. From the momentum equation we mentioned, we can also get pressure gradients. And then when we combine in the energy equation, what we mean when we solve for that is we're generally trying to look for the temperature distribution for all the points in our domain as well. And so they're fairly complicated equations, right? So in solving them, oftentimes we'll make simplifications. So the Boussinesq approximation here is one way we can simplify these equations. And Boussinesq suggested that the density changes in the fluid for certain scenarios can be neglected, except for the gravity term where we have rho multiplied by g. Okay, so in this section here, we're going to look at the simplifications that result from the Boussinesq approximation, and then the resulting equations that we have because of this approximation. Again, this is something you may see come up sort of depending on what field you work in. So it's nice to talk about this to know what this means. So if we apply the Boussinesq approximation to the continuity equation, which is our mass balance, right? That means we neglect the density changes. So that just goes from our continuity equation here down to what we've seen before as our incompressible form right here. And remember that we're not saying that the density is considered as being constant along the direction of motion, but just that the magnitude of this term is small in comparison to magnitudes of our velocity gradients, right? So that's a simplification that we're making. And we can think of lots of situations where density variations cannot be neglected, right? Flows with high Mach numbers, because compressibility effects are large when we have very high Mach numbers, right? So very quickly moving flows, because there are large pressure changes that that then cause large density changes. Generally speaking, we don't really have to consider these compressibility effects when the Mach number is less than 0.3. That's sort of a rule of thumb, which is approximately speeds less than about 100 meters a second in air. And then for water, usually the speeds that are achievable are much lower, so the incompressibility assumption is usually very good in liquids. We also might have to consider compressibility effects when we're looking at very large scales, right? So large that the hydrostatic pressure variations causes large change in densities as well. So there's a number of different situations where you would have to consider the density variations, something to keep in mind, right? Okay, now let's just consider that the compressibility effects are small and say that the density changes are caused by temperature changes alone, okay, like in a thermal convection problem. So in this case, our Boussinesq approximation applies when the temperature variations in the flow are small. So we can assume that our density changes with temperature according to this expression here, okay? Alpha is known as our thermal expansion coefficient, and it equals this. So it gives us this ability to compare changes in density to changes in temperature. So for a perfect gas, that's typically in the range of around 10 to the minus 3. For typical liquids, that's approximately 10 to the minus 4. So even with the temperature difference of like 10 degrees Celsius, the density change can only be a few percent at most, right? Okay, now it also turns out that this term here can also be no larger than a few percent of the velocity gradients. And to see this, we'll look at a scaling argument. So consider that our flow field has a length scale L, a velocity scale U, and a temperature scale delta T. Then we can look at the ratio of the magnitude of these terms in the continuity equation. Okay, so we simplify it to look at how each of these terms scale. We want to look at the magnitudes, right? So we sub in our velocity scale, right? Our length scale, density variation. That all simplifies out to this, which we've seen equals this term right here, which we know is very small. So we write that much, much less than 1. And then that's what allows us to replace the continuity equation here with its incompressible form right here. Okay. Now looking at the momentum equation, because we can use the incompressible continuity equation, we can simplify the stress tensor as we've done previously, right? So we saw that in video 4. So we can write our equation of motion like this one right here. And we can consider a hypothetical static reference state where our density is rho naught everywhere and our pressure is P naught, a function of Z, so that we have this. So if we subtract this state equation from this equation here, and then we write the following, we'll end up with this equation here. And then if we divide by rho naught, we get this equation here. Okay, so we have this term right here, right? This rho prime, the amount that our density changes from our reference state. So our density variations would generate only a small correction to this inertia term and can be neglected here. However, the buoyancy term right here is really important and we can't neglect it there. Like we know, for example, these density variations, this buoyancy is what drives convective motion when a layer of fluid's heated. So the magnitude of this term is therefore the same order as the vertical acceleration or the viscous term. And so that's how we conclude that the density variations are negligible in the momentum equation, except where we have this rho multiplied by this g, right? Okay, now we're going to apply this Boussinesq approximation to our heat equation next. Now, one thing we start by noting is that even though the continuity equation is approximately del dot U equals 0, the volume expansion term right here, where this shows up, it's important to note that that's not necessarily negligible compared to our other dominant terms in this equation. Only for actually incompressible liquids would we consider that negligible. Okay, so we can take this and then rewrite it like this. And this substitution here, we just note that's coming from our continuity equation, right? When we can sub that in, that's what del dot U equals according to our continuity equation. And we've got our thermal expansion coefficient showing up again. So I'll write it out here again to make sure it's really clear what this is, right? Okay, so when we simplify that, right, we have the thermal expansion coefficient showing up there. Okay, so now we've expressed this negative P del dot U term like this, but we can continue to simplify it even further. If we assume it's a perfect gas, we would then have P equals rho RT. Cp minus Cv equals R. And alpha equals 1 over T. So subbing that all in, we simplify this equation right here like that. Okay, so our equation then simplifies to this form right here because we subbed this in right here. And quick note, we used that E, our internal energy, equals CV times T, temperature, for a perfect gas, but we would have actually gotten CV here instead of CP if we just omitted the del dot U from our earlier equation. Okay, so there's a difference there. Now we're going to take a look at viscous dissipation under the Boussinesq approximation. So we compare the magnitude of our viscous heating to the left-hand side of this equation here. We'll do that on this line down here. We'll make substitutions for it again, right? And do our scaling analysis. So we look at the magnitude again. So we make our substitutions here, which we've seen done previously and on previous slides. And we sub in for our scaling arguments, right? Our velocity scale, our length scale, so we sub all that in. A reminder too, when this new term shows up, I don't think I put that on the last slide, but that's this expression right here. Okay, and in most situations, right, the value of this right here is extremely small, approximately, say, 10 to the minus 7. So that shows that we can neglect viscous dissipation in these cases where we can make the Boussinesq approximation. We can also assume Fourier's law of heat conduction here. And so if this K equals a constant, then our heat equation reduces to this much simpler form here that I'll box right under Boussinesq approximation, where this kappa that's included in the equation is defined as this K over rho Cp grouping here, which we call the thermal diffusivity. Okay, so in summary, the Boussinesq approximation applies, like we said, in cases where the Mach number is small, we're not considering like propagation of sound or shock waves, the vertical scale of the flow is not too large, and the temperature differences in the flow are small. Then the density can be treated as a constant in the continuity and momentum equations, except in the gravity term, right? Properties of the fluids like mu and K and Cp are also assumed constant in this approximation. And so we end up with a much simpler set of equations that we've shown here in this section. And this is something you might see show up when people say they've used the Boussinesq approximation. To simplify the equations, now you'll know why. And now you'll know if it's valid for certain conditions that you might be looking at, right? Because there's work done showing how to work with these more simplified equations, right? It makes the math easier. Okay, so now we've looked at the conservation laws, we've looked at how to derive these equations, and I've talked about how these are the equations we'll want to solve to figure out what's happening within our fluid. Okay, the velocities, pressure gradients, temperatures, all these things can be solved for at each point in our domain with these equations. And then we just looked at an approximation we can do to make the math a little simpler in the Boussinesq approximation. Ultimately, to solve them though, we have to have boundary conditions, right? It's a set of differential equations that we're looking at now. So we're going to need, we know, boundary conditions to solve these, okay? So this is the final section we're going to look at here for our conservation laws, because this wraps everything up. Now, firstly, we'll talk about how the Navier-Stokes equations are in a form that requires the velocity vector to be given on all surfaces bounding the flow domain. Okay, so I've made a note of that here, right? So to properly formulate our problem, that's something you'll have to make sure you define on your boundaries. If we're solving for an external flow, so like flow over some body, right? Like flow over a cylinder or flow over a wing or something like that, we have to specify the velocity vector and the thermodynamic state on some closed distant surface, okay, to make sure we can solve the equations. Now we're going to look at if we have a solid boundary, or say the interface between two immiscible liquids, we can actually derive our boundary conditions from our three basic conservation laws as follows. So we're going to look at this picture here, right, where we've got this little pillbox, and it separates medium 1 from medium 2, and we've got our end faces, dA1 and dA2 shown there. They're separated by a distance L. So we want to apply our conservation laws to this little volume defined by this little pillbox. So then we're going to let L go to 0, but we keep A1 and A2 in their different separate media. So all the volume integrals go to 0. The integrals over the side area, which is proportional to L, goes to 0 as well. We're going to define our unit normal vector here, normal to the interface at the pillbox and pointed into medium 1. So our mass conservation would give this. At each point on the interface as the end face area becomes small. And then if medium 2 is a solid, or if it's immiscible, U2, right, has to equal 0. Because you can't have any mass flowing across the boundary surface, right? So in either case, whether it's solid or immiscible, we're going to end up with this condition here. Right, our U1 direction, normal to the interface, right, has to be 0. We can do the same procedure for the integral form of our momentum equation, which says that the force per area on the surface, which is Ni tau ij is continuous across the interface if surface tension is neglected. If surface tension is included, there would be a jump condition, and we'll look at that on the next slide. So we say that this is continuous. And then if we apply the integral form of the energy conservation to this pillbox of infinitesimal height L, it gives our result that the heat flux across the boundary is continuous. Across the interface, or explicitly we can write this as follows. Okay, that must be true at our interface surface. So the heat flux must be continuous at the interface, meaning the interface itself can't store heat. And then we need two more boundary conditions are required to completely specify a problem that don't result from the conservation laws. And these boundary conditions are the no slip condition. So we say that no slip of a viscous fluid is permitted at a solid boundary, meaning that this must be true. Right, T shown here is our tangent condition. So at a solid, right, we can't have any velocity in our medium 2 because we're saying medium 2 is a solid. So therefore, we must also have zero velocity at the interface itself in that tangential direction. Okay, and we're also going to say we're not going to permit a temperature jump at the boundary as well, okay, which would mean T1 equals T2. We do have rare cases where it's not true, where you might have slip along the boundary, but those are fairly rare cases. Although you might come across that, right? So it's interesting to know that this is how that would influence your problem. Temperature jumps as well. Temperature jumps, actually, I did a little bit of research on this. They've been seen in cases where there's a non-equilibrium condition across an interface. So, for example, something like a phase change or something like that could potentially generate temperature jumps at an interface. Okay, so these are the boundary conditions here that we would use to solve, and they would depend, of course, on the scenario that you're looking at, right? You'd be able to apply your specific boundary conditions to solve for your domain that you're looking at. Now I want to look at jump conditions as well, because this is something that could happen in advanced fluid mechanics cases, and I like to look at it. Some of my past research was looking at it as well, so it's something that I'm interested in as well. Okay, so we write it with these sort of double brackets here. And what that's saying is the value of this variable on the plus side minus the value on the minus side. Anytime you see those double brackets there where we're showing plus side and minus side according to our figure here, where we have this sort of n outwards normal, right, pointing away from this interface. And anytime we write this del S, we consider that to be the surface gradient. So then we can again look at each condition, right? So we have the mass condition here. These are our jump conditions. So V is the velocity of the fluid, and we're actually showing you here, that's the boundary speed. So there's different cases where you might have jump conditions. Crystal growth is an example of them, or like I mentioned, phase change, right? So we're showing a boundary speed here with this U. So in this case, the boundary itself could be moving, right? As different from the boundary conditions we looked at previously. You've got momentum as well. So these are the complete boundary conditions here. A lot of cases where these things might not apply, right? This is really the complete condition. Slightly different notation too. That's why I've listed it all here. So B is like gravitational body force. And then we've got magnetic body force. We've got stress tensor, interface stress tensor, Maxwell stress tensor, and the surface tension for a mixture is this gamma. So for example, like this term would go to 0, right? If you don't have any like electromagnetic. Forces. This here is actually showing that's our mean curvature. Okay, so that's a complete condition there. Now we can look at energy as well. Okay, so I'll show a few of these terms right here. So this right here, this epsilon, is our internal energy density function, which is like an interaction with other species. And where you would go into a lot more detail in this is if you took like a graduate course in transport phenomena, for example. You'd spend a lot more time with this. I'm just sort of giving you an overview here so you have them just in case you need them. You might need to look a little more deeply into them as well in like a transport phenomena book, for example. This will often be considered 0 for cases that I dealt with or that you might deal with. This is the electric field. We have the magnetic field as well, which often can go to zero. I'm just putting that as an example, right? Like you might have to consider that, so maybe it doesn't go to zero for your cases. This right here, C, is our mass fraction. When you're dealing with a mixture, right? So this equation is very complete. We might have this stress due to the electromagnetic forces. That will commonly go to zero as well. And then this alpha, right, is representing like each component. So to write a complete equation, if you had multiple components, you would write that expression for each one. So alpha would be each of your components that would show up there in that equation. Okay, so that just completes everything about our conservation laws. With these boundary conditions, I've shown you the jump conditions as well, which is a little beyond what you see in most fluid mechanics books. But like I said, it does show up in transport phenomena, and it can be important. It really just depends on the problems that you're solving. So I just want to show that here so that just in case you did have any jump conditions, you'd know to be aware of them, and you'd know to go and look that up and figure out how to apply those on your boundary conditions as well. Okay, so in summary, what we looked at in this video is we wrapped up our conservation laws section. So we looked at the mechanical energy equation, which showed us how energy changes forms in a fluid element based on things like deformation and viscous dissipation, right? Where you're converting between, say, kinetic energy and internal energy. We looked at the first law of thermodynamics. That was our thermal energy equation. And what we did there was apply an energy balance, and that would help us solve in our fluid. We would be able to solve for like temperature as well, whereas previously our mass balance and our momentum balance would help us solve for velocity and also pressure gradients, but now our energy equation can help us solve for temperature too. We looked at the Boussinesq approximation, which is a way of simplifying our equations that shows up somewhat commonly, so it's good to know what that means. And then we talked about the boundary conditions, right? So to solve all the equations we derived here from our conservation laws, to be able to solve that and, actually calculate what our velocity is, what our pressure gradients are, what our temperature is, you'd have to apply boundary conditions, right? Because we have now the differential form of these equations. So we solve our equation by applying our boundary conditions. And so we looked at what those boundary conditions have to be to formulate our problems properly. Okay, so that's all for video number 5 in advanced fluid mechanics. Thanks for watching.